It's my pleasure to welcome you all back after lunch, and just the level of conversation and the difficulty with gathering everyone back here just demonstrates, I think, actually the kind of the real buzz that there is around this discussion meeting, and that lots of people are having really good conversations, and I certainly have during the break. So for those of you who don't know me, I'm Melanie Wellham, Interim Chief Executive of BBSRC, and I've learnt a huge amount already at this meeting. My own background in research is in mammalian cell biology, although I did spend 18 years in East Anglia living on a farm, so I'm very well aware of some of the issues and problems that we've been discussing and the opportunities. And I think I'm sort of reflecting on it, thinking my father, who passed away a number of years ago, would be really amazed by what's possible now and what might be possible in the future, because I just don't think he would ever have considered that we'd be able to use technology in the way we are today. So I think it's really exciting, and it feels like this has been a really opportune moment to actually have this meeting, and I'm really, really encouraged about it. So I'd like to introduce this afternoon's speaker, Professor Simon Blackmore from Harper Adams University. Simon has a long history of working and pioneering, really, sort of precision engineering and precision agriculture, and sort of bringing the experience that he's had from working overseas in Europe and Africa to really think about how we can actually start to solve some problems in different ways using technology. And Simon's presentation is called Farming with Robots, and so he's going to bring an academic perspective to the meeting now. Thank you, Simon.
Thank you, Melanie. Okay, well, good afternoon, everybody. Thank you very much for the invitation, and the Royal Society and the Satellite Catapult. Dare I say, now for something slightly different, because I think this morning we've seen a range of issues and opportunities from the different sectors. It's always exciting talking to people from other sectors. They come up with different ideas, and we get some quite interesting and mutual sort of synergy. But I would like to extend your awareness of some of the technologies that are now becoming available. As a research professor, I'm interested quite often in terms of technology push. How far can we go? But it is still to do with precision farming, so dare I say robotic is sort of an ultimate form of technology for precision farming. And I am an agricultural engineer, which is then 60% engineering, 40% agriculture, and I have a foot in both camps then. So, just briefly, many people haven't heard of Harper Adams University. We're only a small university, but we're winning all sorts of prizes at the moment, so we're University of the Year from student feedback. We set up the National Centre for Precision Farming, and we've got a range of projects on the go at the moment. I'm not going to go into detail with any of these. So drones are a hot topic at the moment. We're now setting up the Agri-Drone Centre. We've got an autonomous tractor that we can use. We're working on laser weeding, robotic seeding and spraying, phenotyping, mowing, strawberry harvesting, and a particular project that's going to be quite interesting is the hands-free hectare. If we've got all this smart technology that can drive around by itself, can we grow a commercial crop for 1 year without anybody ever going in there? So it's a little bit like the sort of one of the grand challenges for agriculture. Another exciting development is the Agriculture Engineering Precision Innovation Centre, Agra Epi, where a range of companies and groups and organisations, particularly SRUC, Cranfield and Harper Adams, have come together, and some of us here are then involved in developing it, but it still is very new, only approved a couple of months ago, and we're getting all sorts of new buildings and new activities. So hopefully this will be able to give us a platform within which to continue a lot of this interesting work. And that's the current status of the Epicenter building at Harper Adams. So back to topic. Farming in the future. So we're trying to see what technologies we've got available to us. We've heard a lot about Earth observation from the remote point of view. A lot of my work tends to be near Earth. But I do like to think that what we're trying to do here is to develop a new system. And so therefore we need to put our systems hat on to be able to look at all the different implications and opportunities. We look at the drivers for change, sustainable food, improve on-farm economic viability, reduce environmental impacts, legislation, energy prices, volatile weather, competition of world food prices and so on, are all the issues that we have to deal with. And I believe that the current mechanization system that we use does not give us the flexibility that we need. And we've identified various weaknesses within the current farming system. Compaction, the loss of organic matter, coming to the end of economies of scale. I'll cover some of these ones in more detail, but the point is that the crop production system has got to become a lot more flexible and efficient than it is at the moment. And you heard many speakers this morning talking about different aspects that, or dare I even say problems, that we can address by looking at this new mechanization system. So if you've got farms like this, then I would suggest that the mechanization system that we use now is a little bit like an industrial production line, where farmers are dealing with trying to maximize production. And that's what a production line tends to do. And we're using large tractors doing the same work everywhere and based on blanket application of energy. But in fact, industry has already moved round into flexible manufacturing, which then can react to changes in near real time based on current conditions. I'm not talking about the plants and the crops and so on, because we cannot change that once the seed's gone into the ground, but the management and the tools to be able to carry out that management, i.e. the machines, are limiting us, are stopping us from doing the things that we want to do. And it's inevitably going to become more information intensive. To maximize gross margins, manage risk, minimize environmental impact, and automation are all of the factors that go together in terms of this more information intensive. As an agriculture engineer, and many male farmers like their big toys, toys for boys, and machines have been getting bigger. I'm sure those that have been at the cereals will have seen tractors bigger this year than they were last year. But they've now reached their maximum size. Tractors have now reached the maximum size, and it's got nothing to do with agriculture. It's to do with railway tunnels. Have you ever wondered why the chamfer on the top of the combine harvester is there, why it's that shape? It's to fit through the gauge of railway tunnels, because when they're made in one country, they need to be shipped on trains to another country, and they've got to fit through the railway tunnels. The tractors are now the same size now. They can't be made any bigger unless you start assembling them in the field. So big tractors and big implements, increasing work rates, and we have then economies of scale. And it's effectively about the cost of the driver and the cost and time per hectare. Large capital investment, and we've reached the maximum size. It's good for large fields, cannot be used in smaller fields. Now, here's an interesting idea I'd like to get you to think about, and maybe we can discuss afterwards. Where is this extra production going to come from if we're going to feed the planet? The big farms and the big fields, I believe, are very efficient with the big tractors and the big equipment. But I now am starting to believe that the small to medium-sized farms and fields have the greatest potential for increased production with appropriate technology. So where we don't want to rip out the hedgerows through environmental aspects or any other reason, it is those areas that have got the biggest potential for increase in food production by using appropriate technology. We've heard some discussion this morning already about compaction. Here we have sugar beet, where the root's being constrained by the plough pan. But please consider that we now estimate up to 90% of the energy going into cultivation is there to repair the damage caused by the large machines in the first place. Tillage, ploughing, harrowing, cultivating. We do that every year, don't we? Why do we do it? Well, we've always done it. Why do we do it? Because we've always done it. Why do we do it? We need to realise that the repeated damage year after year, plough damage, plough damage, plough damage, is a total waste of time. And in fact, what we need to do is less. And it's not often that we come up with a conclusion like this. Best thing to do with soil is leave it alone. Don't damage it in the first place. You don't have to repair it. Where do you find the best soil structure in the natural environment? Anyone? Dick?
Under the hedge.
Okay, thank you. Under the hedge or in the forests, where the natural flora and fauna create the right soil structure. So if we leave the soil alone, we can then, don't need to repair it. The natural soil flora and fauna produce ideal soil structure. Let the worms do the work. So a lot of these things that you'll see in terms of this new concept, in fact, there is nothing new here, because quite often we're looking at the things that maybe our fathers or grandparents used to do, but somehow we seem to have forgotten a lot of these factors. But with the new technologies, we can do it in a different way. And we have also heard about controlled traffic farming, but I'd like to also consider ultralight machines that don't cause compaction in the first place. So that brings us on to the concept of farming with robots. So here we've got some pretty red robots here. This is all computer graphics, but it allowed me to be able to express the ideas that I had in terms of developing a complete new mechanization system that could deal with all of the problems that we've got now, and also then deal with all of the drivers for change that farmers are experiencing. And it gives us the ability to have this much more flexible system. And it falls into four main areas then: establishment, crop scouting, crop care, and selective harvesting. And I'll go through each one of these. So it's a systems concept to help improve or make production agriculture significantly more efficient. It's very nice to hear about the opportunities we've heard this morning, 3%, 8%, 10%, 20%. You'll see some drastic figures in a moment. Increased production from the smaller fields, and if we want to feed the planet, we have to consider agriculture around the world, and specifically I do a lot of work in China and Asia now, and the average size of fields there is about 1 acre. So they cannot use economies of scale there, and they don't have necessarily the technological support with the sort of technologies that we've got at the moment. We need to make money, and so reduce the cost of food production, reduce the energy needed in agriculture. We use huge amounts of energy in all the different forms, whether it's a big tractor, whether it's chemicals, fertilizer, whatever. And we throw that energy all over. We throw it here, we throw it there. How much of that actually goes on target? 10%, 20%, very small numbers. So we need to come up with a different paradigm, and particularly then all of that waste then is causing problems with our environmental services. But the interesting thing is, when I'm talking to, there's nothing new here for the tractor manufacturers. They know all this. I've spoken to them endlessly. They're not interested because it's too disruptive. The idea of being able to develop robots to go and do the same task that the big tractors do, no thank you. We're busy doing other things. The long-term plan is to change the market share from 32% to 35%. And the idea of going into developing robots, no, not interested. So heads in the sand at the moment. But I can put my hand on my heart and say there will be agricultural robots, but whether they'll be in 2 years' time or 20 years' time, we'll have to wait and see. So here we have an ultralight seeding robot. So It's not particularly difficult. Here are some of my master students. I challenged them to find a machine that had less than 40 kilopascal or 6 psi pressure underneath the contact patch of a vehicle, and then to robotize it. And so they've put all of the control system on there for steering it. Now the interesting thing is that this was done, the tests, in February, a couple of years ago, and at that time of year it's very wet. The soil is at field capacity. One small bit of science then to remind you, field capacity is where we've got the soil, you put a litre of of water into the soil, and a litre of water comes out. So it's not flooding, but it cannot hold any more moisture. But that is then where the soil is very, very weak. And so this tractor was running around when the soil was very weak, and I went to step out there to have a look at the machine, and as I stepped out, my foot sank into the soil. And I thought, gosh, I'm not going to make it to the tractor. It's too wet. And the following day, you maybe just see that little puddle. That's the infiltration. So it rained afterwards, the soil was compacted just by my footprint, and the water could not go into the soil. Think about all the issues of flooding. Think about all the issues of water tables and so on. And if we can come up with ways in which we can deal with better infiltration rates, the water goes into the ground level, we don't get such issues with flooding. But where the tractor went, up and down here, there is no flooding, no puddling on the surface. And what that's telling me is that the tractor was able to run around at field capacity without causing any damage. Okay, so you then say, so what? Well, so what means that the farmers now have got the ability to put seed into the ground when they want to put seed into the ground, meaning that agronomy is then going to be the limiting factor, not the tractor. Say if you want to put sugar beet into the ground when the soil temperature gets to 4 degrees C, you then want to put seed into the ground. You can't do it at the moment because the tractors that we currently use would sink up to their axles. But we need small ultralight machines that can run around and be able to do this. Hence this concept of more flexible approach. So if we talk about crop scouting, there's a lot of interest working with agronomists to give near real-time data over the whole farm. We've got unmanned ground vehicles. There's a lot of interest in the UK at the moment in terms of all the phenotyping robots. We've just got a contract in working with Australia to develop a phenotyping robot for grasses. Scouting robots, it's just a subset of the phenotyping work. And of course UAVs, which is what I call a rapid assessment technique, which then allows us to very quickly go over a field and get all sorts of high-resolution imagery and non-visible images and data. The sensors are usually limited by weight and power, but this is a rapidly changing area. No doubt you've all seen drones in the papers, and maybe some of you have got them at home and farmers are investing in them. These are all what I call first-generation drones. But we're now working on second-generation drones, and these drones will actually do things for us. So it's a very active group within the special interest group, the Drones for Farming. We've done courses, agricultural training for drone pilots, picocopters, tiny ones up to megacopters, and a whole range of other opportunities for these second-generation drones. We're now setting up the Agricultural Drone Centre. That one's a little bit difficult to see in terms of scale, but that's about 2 meters across there. That's a dangerous machine. But you can see that it does have the tanks underneath here and sprayers. So this is made in China, and they want to sell it in the UK. But the interesting thing is that most of the legislation that we've got for application of chemicals is defined by the way in which those chemicals are applied, meaning you've got a big sprayer and spray booms and you're squirting chemical out all over the place. But I'll show you an example in a minute where we need to change the law to be able to come up with more targeted approach. But nevertheless, this is still a classical method at the moment, and we're then developing a system to be able to work. Well, we're collaborating with the Civil Aviation Authority. They're very supportive of drones in farming, so long as that it's done right. Chemical Regulation Directorate are also very supportive, and these drone companies. So we're setting up some spray testing laboratories to see how well they can work. A ground-based scouting robot then was developed a couple of years ago. This one is now at the University of Athens. And that's then effectively carrying a range of different sensors on there. We can fit a whole range of solid-state non-contact sensors on there. They're looking at thermal cameras for irrigation status, multispectral cameras for nutrient status, and LiDAR for canopy extent and density. So robotic weeding. Here we did some physical weeding systems with the autonomous tractor. This was the first one that I made. So RTK on the tractor body, RTK on the side shift toolbar, and then this is a cycloid weed hoe. It's not rocket science, it's robotics, I tell my students. It's just good engineering. We know the position of every seedling that went into the ground because we recorded the position when the seed dropped through. Cut a light beam, recorded the position. RTK gives us accuracy of a couple of centimetres, and we can then go into this and be able to go around the lettuce plants to be able then to avoid them. So purely deterministic. There's no artificial intelligence in there. But the interesting thing is we're stirring too much soil here. We're wasting a lot of energy more than we need to. So here we've got a PhD student, one of my old PhD students working in Denmark. He developed the Microdot sprayer. There is a commentary to this, but I'll just talk over it. So here we've got a token weed here, and we've then got a hood here with LED lights inside there, a camera on the top that's then looking down, and then underneath there
we have a microspray.
Okay.
The black box here,
thank you very much.
which have 7 distinct nozzles, which can apply herbicides individually. And now let's see how it works. We place the plant in this holder and then start the robot. And now it's moved into the tunnel, and on this screen we can see what the camera sees.
So you can see it's just a laptop here, it's not a supercomputer.
Now you can hear that herbicides have been applied. And on the plant we can see that the blue stuff, which is the colored herbicide we have applied.
So all that we're doing here is just using a bit of smarts, but it's giving us the ability to be able then to make sure that the chemical only goes 100% on target. And if we can do that, how about reducing our chemical usage by 99%? We're not talking of saving 1%, saving 2%. How about saving 99% by volume? So, what are the implications of that? Well, we are carrying out some extra tests at the moment with Syngenta to be able then to see how relevant this is. But this is the video that most farmers love because here we've got some more weeds, and we're getting the lightsaber out, and we're giving them a good going over. Of course, I'm absolutely horrified that they should have exposed lasers like this. We don't do things like that in this country, as are all locked up properly. But the interesting thing here is that, yes, these are then little weeds. This is then a full-size weed to me. And what we do is that we heat up the meristem, the growing point, to 95 degrees C, and the cell walls then rupture. And the weeds then, there's no no visible difference here. It's only using tiny amounts, small number of joules of energy to then kill or retard or make the weed go dormant. And again, next month we're doing a lot of work with G's at the moment, and next month we will have a laser weeding system being trialled at G's to see whether this actually works or not. It works in the lab fine. Can we then make it work in the field? And then we have got the autonomous tractor, and this is just a video of it working normally with GPS, but we've got something called LiDAR underneath here, and we can then measure the gap through here, and the tractor can then change its steering and adapt. So this tractor is then designed to go into orchards, and we can carry a range of different sensing systems to be able to measure different things in trees. Which finally brings us on to selective harvesting. Between 20 and 60% of the harvested crop is not of saleable quality. So between 20 and 60% of the harvested crop is thrown away at the point of harvest. Why? Where is the problem? Dare I say, you are the problem. All of you in here, it's you lot and me. Why? Because when you go to the supermarket and you see a lettuce on there, why don't you pick the worst one? You pick the best one. And the supermarkets say, okay, that's fine, that's customer behaviour, so we'll pass that straight back to the farmers. So if the lettuce is slightly small, or if your cucumber has got the wrong curve in it, then they won't accept it. So there's two options then. Either we change, and I don't fancy the chances of us changing, and the other way then is to do what we then call selective harvesting. And now that's giving us the ability to only harvest that part of the crop which has 100% saleable characteristics. And again, it's offering a new opportunity for phased harvesting, pre-harvest quality and quantity assessment, grading, packing and sorting at the point of harvest to add value to products on the farm. Grade for quality, sweetness, ripeness, shelf life and protein. And another project we've got at the moment is robotic strawberry harvesting. We can pick the strawberry and we can grade the strawberry at the point of harvest. This is a Waitrose strawberry, this is a Tesco's strawberry. This has got a shelf life of 3 weeks, this has got a shelf life of tomorrow, this one's really sweet, this one's not ready. So we can add value to products at the point of harvest and minimise the off-farm grading and sorting and help the farmers to be able to make more money. So here we've got the concept of the vehicle. So here's the harvester. This is the trailer, if you like. When this is full at the back here, it disconnects, runs off, another one plugs itself in, and underneath here it's then got all the logistics, the fuel and water and so on. But we've left behind the smaller lettuces. So rather than harvesting them and throwing them away, let's leave them there and come back next week when they've grown to the right size and then harvest them again. Lots of different things here, different ways of doing things. I'd be very happy to have discussions on the implications and how some of these things can actually work, but I know that I've run out of time, so I will leave it there and say thank you very much for your attention.
So thank you, Simon, for some very thought-provoking ideas, I think. And I noticed that you had Massey Ferguson on there. Is that wishful thinking, or are they actually going to be taking
they paid for the graphics.
They paid for the graphics, okay. But will they be taking up the concept of the robots?
They will do when they've learnt the lesson.
When they've learnt the lesson. I think we have a few moments for a couple of quick questions. If anyone would like to ask Simon anything, yes. Question just here.
Hi there, my name's Megan Darby. I'm a journalist for Climate Home. I write about climate change and I'm more familiar covering energy than agriculture. It can be kind of on the sidelines of that discussion. But a lot of the technology you've described involves huge resource savings or by targeting stuff a lot more clearly. I was just wondering if you'd done any specific analysis on the carbon footprint savings of some of these technologies.
The simple answer is no, But as an engineer, we like efficiency. We understand efficiency. And what we've really tried to do here is to apply those same principles to the crop production process. So whether it is then a saving in terms of money, whether it's a saving in terms of energy, if we can reduce the amount of inputs that we use, then it's going to have all of these ramifications for the environment, for carbon, for economics and so on. But the point of it is that we can't just reduce it everywhere. We need to increase it in some places and decrease it or cut it out in other places. So the whole concept of all of these machines is based on what I call intelligently targeted inputs, meaning we've got to have sensors there to understand the growing environment and the particular area that we're interested in, and only do the minimum amount or introduce. One of the aims for all of this work, what is the minimum amount of energy that we need to introduce into the natural environment to turn it into productive agriculture? That's my aim. I don't know where that is or what the implications of all that will be. But any time that we have energy that is being wasted, it's not a good thing. Farmers are buying this energy, they're buying the chemical, it's wasting, it's polluting, and so on. So it's just it's following the ideals of precision farming, but it's just doing it in terms of trying to come up with the machines that can do it in a much smarter way.
Okay. Thank you. I think that probably in view of the timing that we leave it there,
Okay,
and thank Simon once again for his presentation. Okay, so we're now moving on to our sort of round table, our discussion sessions around the tables, and hopefully for those of you who are listening just before lunch, you will have selected the table which has the kind of the topic that you're most interested in discussing. Don't worry if you haven't, you have an opportunity to move around. On each of those tables, there is a facilitator and there is also a note taker. We would like you to spend about 25 minutes having the initial series of discussions, and there are some questions to prompt your thinking and your discussions associated with those topics. About halfway through the session, so after about 25 minutes, I'm going to make you aware that should you wish to move around to another table and discuss another topic, then you can do that. Facilitators and note takers, please don't move, stay where you are, otherwise we'll lose the whole thread. So there's some freedom of choice there. And then after about another 20-25 minutes or so, what I'm going to do is to ask the facilitators, and we'll start at this table down here and go in a zigzagging pattern towards the back. So this table number 2 will need to be prepared to go first. You can have a minute, so you probably can make 2 or 3 points that kind of sum up the key elements of the discussion that you've had. But hold on to some of the other points, because after we've had our next break and networking session, we'll come back for a panel discussion, and I'm sure that there will be things that will come up at your tables that you will then actually want to bring to that panel discussion. So bear those things in mind. So hopefully that's all fairly self-explanatory. I will give you a signal after about 25 minutes so that you can move around. It seems like a long time, but believe me, these sessions will just go really quickly. So you're going to have to be thinking about what your key points are, and I'll give you a 5-minute warning before we get to that point. Thank you all.